Welcome back, everyone. We have three more presentations for you, three exciting projects from three amazing speakers. To start us off, our next presentation is about a software that has been mentioned throughout the day, here to give you a strong understanding of ChainBridge and what it's all about, ChainSafe's very own Polina Aldina with ChainBridge 101. Polina, why don't you join me on the main stage here?
I'm trying.
Hi, Polina.
Hi. Oh my gosh. Here we go.
Yay. There you go. How are you doing?
Yeah, doing good. How are you, Dustin?
I'm doing excellent. Well, the floor is all yours, so enjoy.
Thank you so much. Let me try and share my presentation. Pardon for the background noises. I have a dog. Okay, I hope you see my screen now. Just will check the chat for yes. Yes, awesome. Okay, so hi everyone, my name is Polina and I will tell you the awesome story of ChainBridge. But to start with, the main hero would be myself, for now at least. I was working in blockchain for about 5 years and started with Ethereum when it was around 13 or 17 bucks per ETH, and everything was really cheap and awesome and not stressful, and you can just deploy everything on mainnet and be happy. And do tokens easy and all the things. And then came the DAO, and then came the ICO wave, and then all of us got to feel the need for scaling. And the product that I was working on was a decentralized exchange. And it hit us rather bad because the limited volume of transaction, and they cost a lot, they take a long time to happen, and it wasn't cool at all. Also, CryptoKitties happened, and the solution that we thought would make a lot of sense is just get exchange deployed on another public network that is scalable. However, having all the assets, like if you see the graph on the right, having all the assets on Ethereum mainnet implied the need for the bridge. And we didn't really find a solution back then. And somewhere around exactly that time, ChainSafe R&D showed that a lot of projects were interested in bridging. So ChainSafe started building a bridge. And sometime after that, I've joined this awesome company, ChainSafe. And I see that they believe in open source and drive the most awesome stack of projects possible, well, from my perspective. And yeah, basically the infrastructural support for Web3. And what an exciting news was to hear that I'll be managing development of exactly the bridge that we wanted back then, but now in ChainSafe. And yeah, the first version was a bit glitchy and very alpha version. We were looking into interoperability right away, but obviously started with EVM support because, well, all the side chains back then were Ethereum side chains. And this is how started the vision of an ideal bridge. And so the ideal bridge is a decentralized bridge that can be accessed anytime with will not have one point of failure and should be easy to integrate with new chains, and transactions also should be very secure and very provable. However, it should not be a blockchain of all blockchains because, yeah, it very much sounds like a blockchain to me, at least. So let's do a small dive, not a super deep dive, on how does the bridge works. And we have two blockchains over here, yellow and white one. And we need to pass messages between them or transactions. So we're adding a layer to do that. And so even better, let's maybe add 3 relayers. So we don't have one point of failure, and we can also add a multi-sig. So we have more additional security and it works smoothly. And to make those relayers actually pass messages, we need to make them work with the chains on the left and on the right. And how do we do that? So how would bridge chain specific components look? So we have a blockchain and a relayer. Relayer has a chain module with 3 components, which is connection, listener, and writer. So connection allows you connect to chain like nodes, And when you're passing a message from one chain to another, you will need to get it from one chain and write on another. So that's why listener specifies what events to listen to and how to handle them, while writer is actually lets you get those event processed and put it on the blockchain. So on the blockchain side, you see that there's like a set of bridge smart contracts or analog like that, for example, pallets on Polkadot. And that side, you will need to implement like bridge logic in the chain itself. And that part will be emitting events that will eventually be listened by the relayer. So for example, when you transfer tokens from one blockchain to another, you have tokens deposited on one chain into the bridge contract, and you see the deposit event, and then you will need to mint those tokens on the other side of a chain. Here you have like listener and writer. So also, as our bridge is like a toddler, it's not fully decentralized, and right now it has a parent, and that is admin down below here. And admin is very chain specific and does all the needed configuration for the specific chain that it administers. For example, registers the relayers, configures methods for listener, and setups fees, also stops or resumes the bridge in case something happens, and so on. So let's see the insights for relayer. It's pretty simple, very much. You have an event going from the chain into listener. Listener have a handler that for each event, there is a handler who knows what to do with that event, and it puts event into message that can be understood by inside of the relayer, and that is a rotor. Then rotor checks the message and sees what it needs to do with it, what chain do they need to relay to, and so on, and then puts it to the writer. And then writer sends the transaction to the chain because writer knows how to send transaction to the chain. So here is how a little bit deeper dive on how the message is bridged. So on the blockchain side, there is a deposit method in bridge contract, and user called this method, and that emits the deposit event. And then relayer, we have, for example, 3 relayers, and we need 2 signatures to make something pass through the bridge. So relayers will listen to the deposit events. Once they detect an event, first relayer who detects the event will create a proposal on chain. The second one will vote for it because he sees the proposal created, he sees the deposit event, he will vote on it. And because we just need only 2 relayers for this specific case, then it will also finalize the proposal. Then, like returning to previous screen, the message will be handled and put into correct format, went through the router and go to the writer and send transaction on the other chain. And that's pretty much it. For example, we can do very specific example with token transfer. So to transfer a token, you first need to approve the bridge to transfer tokens for you, because as a user, you will call the deposit function of the bridge. So first you will send approval transaction, then you'll send transaction to call the deposit method of the bridge, and then the deposit method will emit the deposit event. Within the relayer, a relayer will detect the deposit event, create the proposal, other relayers will sign it. Then this will be 2 additional signatures, because signatures also happen on chain because they signed the proposal that is on chain. So we have 2 relayers in this case. That will be 2 more transactions with signatures. And then there will be the last transaction that is minting the tokens on the blockchain recipient. And that's how the bridge works. This is the bridge, and you can see that everything is pretty modular in here and should be pretty easy to understand. And with this kind of structure, you can see that, for example, if you want to add additional chain to the bridge, it's pretty easy to do because you just need to support this part of modules, and you have blockchain that you can just add up to existing bridges. So the integrations that we're supporting right now, if you want to use our bridge, is everything that is EVM compatible. You can just get our stack of contracts and use the bridge out of the box. Same for the Polkadot parachains. We have a substrate palette. You can just go and use it directly. And just a short summary of what was told here. Sorry for my notifications. Yeah, To add your chain to the bridge, you'll basically implement the chain-specific component that is connection, listener, writer, and on-chain contracts. You also include the handlers for your specific contracts within the listener and writer. Then, you will need to set up the relayers that you want. For example, would you want multisig 2 out of 3 or 5 out of 10, and so on and so on. You will have admin per chain. So for example, if you have a bridge from, I don't know, Cody to Girly, as we have on our test networks, you will have one admin on Cody and one admin on Girly. So you need to be careful with that. And yeah, you can bridge pretty much anything. We have handler implementations for specifically token transfers, which is very Ethereum. But for example, for Polkadot, you can pretty much bridge anything. And generic handler allows for any arbitrary message bridging or whatever additional logic you can implement. Okay, so our bridge right now has version 1, which is fully audited. If you just Google like chain bridge audit, you will find it by diligence. In packages, first one will be the centrifuge. It supports NFT tokens and also passes arbitrary messages to their parachain. And it doesn't really have a UI, and it is within the centrifuge infrastructure. So this graph actually shows the centrifuge infrastructure and bridges over here. So you know, we also have recently launched the EDC bridge. So it is able to pass the wrapped EDC from Ethereum Classic to Ethereum mainnet and trade them on Ethereum mainnet and backwards. And here's just a kind of screencast from our test run for them. And yeah, you can try it out yourself. I'll have links a little bit later. Additionally, we have a bunch of bridges that are in development. We'll also have talks from Edgeware and Ampleforth a little bit later, maybe, tomorrow or day after. You can definitely check out those. And yeah, we have, I suppose, way more bridges in development that we know, because there's at least like 28 forks in the moment of our repository. This is pretty much this is the ones that I know of, for example. So awesome. If you want to actually add your chain, what should you do? First of all, check out our documentation, check out the repo, check out testnet bridge. If you like it or not, you can just click through the UI and see how awesome does it work. The documents cover pretty much all the basics that were included in the presentation and a little bit more. If you're really interested, go see the repo and everything else. If you run into some questions or if you want some help with development, feel free to reach out. The info at ChainSave.io managed by me, so not my personal email, just right out there. Also, if you have like really a lot of questions and you need like very synchronous answer, it's a very good idea to jump at our Discord. All the QRs are like just showing the links. So drop by the Discord, we'll answer questions as we see them. And all right, one more thing. We're hiring. So if you want to work at ChainBridge, specifically or ChainSafe, please come and join our awesome team. And at this awesome point, thanks everyone for your attention. I'll stop sharing my screen and I'm ready for your questions.
That's awesome. Thank you so much, Polina. What a great overview of ChainBridge. I cannot wait to see the future progress of this project. Such an exciting time.
Great.
We do have a question for you in the Q&A. What are some of the biggest challenges working with bridging different blockchains?
Oh, that's a good question. I would gladly ask David to answer it. I guess with different chains, there is oftentimes edge cases with what libraries you use, what kind of dependencies you have, because ChainBridge is actually a lot of DevOps work. So you should know about that. Also, there's not so much troubles, for example, with consensus, but there can be problems with how do you sign the messages, for example, or how do you verify like inclusion, or what would be the block time for a specific chain. So that will be like somehow overview of the challenges that we usually have.
Awesome. Thank you so much. We have one more question for you. What chain do you personally What is a chain you personally would like to have compatibility with?
Well, to be honest, I'm waiting for Cosmos SDK. So we're planning to deploy Ethermint soon. And yeah, afterwards we'll be researching the Cosmos SDK. That's going to be fun.
That's awesome. Thank you so much, Polina. I know you're busy. Thank you so much for taking the time to educate us all on Chainbridge. Our next speaker will be speaking about a project very dear to my heart. You've already heard a presentation about the Filecoin ecosystem today. Now we're going to listen to ChainSafe's own implementation of Filecoin in Rust by our Forest Tech lead, Austin Abel. Austin, go ahead and join me on the main stage by turning on your cam and mic.
Hey, how's it going? Can you guys hear me?
Sure can. How you doing, Austin?
Doing well. How are you?
I'm doing well. The stage is all yours, and we're very eager and excited for the presentation.
Yeah, let me just set up the screen sharing. All right. Can you guys see my slides? Ooh, that's not the start. You guys see my screen? I assume you can. If I don't, then Dustin, I hope you interrupt. So anyways, yeah. So as Dustin said, my name is Austin. I'm going to be talking about Forest, which is a Rust Filecoin node implementation, and talk about some of the lessons learned and challenges that we've encountered. So the three main topics I want to cover today is, first of all, is why we love Rust and how it's allowed us to improve our client, but also improve the Filecoin protocol, our challenges when implementing the node, and then also our progress as we are right now and where we want to go to in the future. So it's become very clear, and I know other people have made the comment of why multiple language implementations are important, but specifically for why we're building it in Rust and why build a Filecoin node in Rust is the two main things is safety and performance. So first, why is Rust safe? So Rust is safe because pointers and their mutability are checked at compile time, which means no null pointers, no double free, no dangling pointers or use after free. There's also no seg faults and no buffer overflows, which if you're not a developer, this may not mean much to you, but just know these are very common issues and lead to security vulnerabilities. Another big point about Rust is that there's no data races, even with concurrent programs. This is specifically important because the current trend with CPUs is that single thread performance is quite stagnant, where the number of cores is increasing. So it's very important that you write very concurrent programs, but also make sure that they're safe. And these memory and safety issues lead to a lot of security vulnerabilities. There's a few organizations here, large organizations, that have analyzed their memory and safety issues with their security vulnerabilities, and the numbers are pretty large. And these numbers definitely aren't decreasing. Just to name a few: Microsoft 70%, Ubuntu 65%, macOS 88%, and Chromium 70%. And this problem just is not solved by just having better developers. This percentage isn't going down over time, and the number of security vulnerabilities is increasing in large software projects. So another reason why Rust is performance. So a main benefit for Rust is that it gets compiled to machine code through LLVM. The profiling tools such as perf, dtrace, and valgrind just work because of this. There's no garbage collection or runtime, so that means no GC pauses, no memory overhead. And there's also zero cost abstractions, which just means it's going to optimize away any unnecessary code. There's also efficient generics, which means Rust will optimize as if there was no generics, and also avoids dynamic dispatch. And specifically for this project, it is quite nice to be able to interact with the Rust proofs without going through an FFI. So for those who don't know, all the proofs for the Filecoin protocol are actually written in Rust, even though the reference implementation is written in Go. So an example of profiling, this is just one example. This is what's called the flame graph. Because dtrace and perf work with Rust out of the box, you're able to analyze what the time spent in the software, which functions that time is spent in. This is especially useful. This is especially useful in software because humans are generally very terrible at guessing this kind of thing and guessing performance of software. So it's very nice to be able to have these tools to be able to analyze and check which parts of the code are taking a lot of time. For example, this is a flame graph that the most recent one I've generated, which is syncing the node for the first 1,000 tip sets. And as you can see, a large portion of it, which I found out, which I wouldn't have guessed, is over 1/3 of it is just aggregate BLS signature verification. So that kind of indicates that we should be moving towards the more optimized assembly BLS verification that Protocol Labs has been working on. So next I'm going to talk about a few of our challenges. So I'm definitely not going to cover everything, and there's a lot of small points and learning aspects throughout the project, but I'm just going to cover three main things, which is the large data sets that are included with the Filecoin protocol, the actors, which is the state transition logic of the node, and then also some things around peer-to-peer networking and async programming in Rust and the challenges around it. So to talk about the data in Filecoin, I kind of want to start from the ground up. So the data representation of Filecoin is represented in this type called IPLD. And this structure may be somewhat familiar, or like some of the types might be very intuitive, but the thing that makes it very different, and the key point of what makes IPLD different from regular just generic value types, is that it has this link option, which is basically what a CID is. It's a content identifier, which is a hash link which links to other nodes, and this basically allows you to link all of these nodes together through those hash links, and then be able to shard the data of the network so that reads are quicker, writes are faster, and you can deduplicate a lot of data. So when you have these IPLD nodes and hash links, you generate what's called like an IPLD DAG, which is just a decentralized, it's an directed acyclic graph where basically you have all of the squares of the IPLD nodes, and then the arrows are the hash links to the other IPLD nodes. This is a very, very extreme simplification of what data will look like in the Filecoin protocol. So for example, you have these blocks together which form what's called a tip set in Filecoin, and those link to the underlying state, and you can represent all that data with just a few cryptographic hashes, and you can resolve any underlying data. And the benefits of this is that if there's any shared data from state transitions over, you don't have to store duplicates of this data, and you're able to, as the network size scales, you don't have to store like exponential amounts of data. And this is very important also for Filecoin, because the deduplication is very important, because the state of the network is very large. The stuff that Filecoin is doing is obviously very revolutionary, but it comes with a price that the state is very large, and there's a lot of computation necessary to do the things needed to have a decentralized file storage protocol. And just to compare this data representation to ETH2, just because I think there's some interesting trade-offs and some things to talk about. First, like IPLD DAG is very generalized, which means that you can use it for anything. You can represent any data with it. It's also the encoding protocol is generic, so you can encode it as CBOR, you can encode it as JSON, you can encode it as protobuf. It doesn't really matter. It's also self-describing, which means if you get a hash link, you're able to not only know what the representation of the data would look like, but also which protocol it is, which encoding protocol I mean, which is very useful. There's also deduplication of similarly typed structures, which, as I mentioned, is very useful because the size of the state is very large. And then also, but the negative to this is that by default, there's less efficient proofs, because to be able to prove an element exists in this graph, you'd have to include all of the nodes all of the nodes up to the root. So to compare this with simple serialize or ETH2's data representation, it's a binary tree with 32-byte chunks, and it is very heavily optimized for Merkle proofs. The reason that this is necessary is because ETH2 has first-class support for light clients, so this needs to be extremely fast, and also allow nodes to not have to store as much data. But the negative to this is that there is some data duplication due to the fact that the types and underlying representation is built for faster Merkle proofs. And also the negative is that you have to know the underlying types of the data, so you can't just resolve and traverse any arbitrary data. You have to actually know what that data represents, which does and sometimes become a negative. So to talk about a few of the challenges with actors, as I mentioned before, the actors is the state transition logic of Filecoin. You can think of actors as somewhat like smart contracts, but that are built in. So they're somewhat like precompiles in Ethereum. In this case, they're written in native Go, so the reference implementation is the specification, which kind of becomes a challenge. So a few of the challenges that we've run into when implementing these, and this has been definitely the biggest challenge when implementing the node, because it is such a large component of the network and has to be very meticulously matched, is that especially when it started, there was a very frequent and fast iteration, which is obviously necessary for the network to become what it is now. But it was very difficult as an implementer to match. It is stable now, but now there's 2 versions to maintain and also a 3rd one coming soon. And another challenge is that it's more than 20,000 lines of idiomatic Go code. So matching that is definitely very difficult. And also, as I mentioned before, the state is very large. Just to give an idea of how large the state is, the minimum proven state of the network to be able to sync on mainnet right now is around 13 gigabytes. So whenever state discrepancies are found, it's very difficult to be able to migrate that state between implementations to be able to test and find out where the discrepancies are. Another challenge with the actors is just that the gas usage, which can cause a consensus fault, is based on the bytes read and written to the database. So it has to be very exact, and even in the case where if you read any less bytes or any more bytes, then there'll be a consensus fault, which is obviously a problem for us. Another thing is just that the language implementation differences makes it harder to do things like error handling, because there's some very idiomatic stuff that's happening, and making sure that for every code path that we have the exact same functionality was definitely a challenge. So what are the things that we did to mitigate these things? So there's a few things, and the main thing that helped us solve these issues and make sure that we have a client that does interop is one, conformance vectors. So these were language agnostic JSON test vectors developed by Raul and the Project Oni team. This has by far been the biggest help for us to be able to solve these issues, and it's definitely something great for any multi-language implementation blockchain to have, is just a lot of language agnostic test cases, because it expands the amount of which you can test at the network that you can't get from just native tests. And we're obviously passing 100% of those vectors. Another thing that's helped us kind of resolve these issues is tools to compare the IPLD state. One of them, which is state diff, which I'll talk about in the next slide, and also setting up tooling to run specific parts of the code. The reason being is that it is a very large protocol, and being able to narrow down certain sections of the code that can be identified as different and running those separate, very segregated was a way that just made it easier for testing. And then also the last point is just expanding Go and Rust testing to track database usages and serialize vectors to make sure that everything was consistent, because those are things that need to be exactly matched. And then also fuzz testing the HAMP and the AMP implementations. For anyone who doesn't know, fuzz testing is basically throwing large amounts of random data at basically software to make sure that there's no edge cases or security vulnerabilities there, which we do obviously plan to expand to more things in the future. So what is state diff? So I mentioned this on the previous slide. This is a tool that we set up to help identify the differences in state between the reference implementation and our implementation. Because the state is so large, it's hard to do this. And because it is sharded, it's really hard to find the differences from just a simple cryptographic hash. So the idea is in 3 parts. So resolve all hash links to collapse the data, find the differences between them, serialize them to JSON to make them more readable, and then compare and print the differences between that JSON. So just to walk through a common issue that was run into, or a common pattern, is whenever there is a consensus fault, all you really get, and this is very consistent among other blockchain projects, is all you'll get is just a cryptographic hash of saying something under this state is different, which isn't very helpful. So the benefits of this is being able to resolve that data and compare the differences. So for example, just with those two links, you're able to resolve into state and then find exactly where the difference is. So for here, it's this one, this is one of the links that's different, and then being able to traverse deeper into that. And this is just a bug I created just to show what it looks like. And then just to see that the actual difference, you can find exactly what in state is different to be able to debug it quite quickly. And that's helped us get to an interop state. So one last thing I want to touch on is just peer-to-peer networking, which was a challenge and definitely a tough thing to do for any blockchain protocol. There are three main ways to synchronize a peer-to-peer network, generally through a distributed hash table or DHT to store key value pairs. There's pub/sub protocols to be able to publish and subscribe to events. And then there's also request response calls to specific nodes where you basically dial a node, send a request, and expect a single response back. The Filecoin does use all three of these strategies with their protocols, and it definitely makes it difficult to make sure that all these are done efficiently, asynchronous, and also make sure it doesn't block any other operation. So this has definitely been a challenge. Fortunately, a lot of the core networking stuff has been handled by Rust-lib P2P, so that was great. And there's a lot of shared tools, and especially since ETH2 is using a lot of common things, and also Polkadot. So also another challenge was that when we started the project, async await and futures were just starting to be stabilized. So we were one of the first to kind of jump on these new futures, and kind of navigating this ecosystem was especially since it was so fragmented, was definitely tricky. And then obviously the last challenging part of mixing asynchronous code is just that you have these long-running synchronous processes, or even some that aren't, like state transitions, proofs, IO, or even shared access through mutexes, and you have to make sure that those don't block and affect any other parts of the code. And obviously this is important because you don't want anything to be slow, or else it can become a DOS vector to take down the node. So now I'm just gonna finally cover a few last points of where we are right now, and where we plan to be, what our goals are for the future. So right now our project status is we're full syncing up to the Breeze fork, which is height 41,280. We are currently in the mix of upgrading from Actors V1 to V2 and supporting both. But for now, that's where we're at. We're passing 100% of the test vectors. We have all the sync protocols implemented, and we have a JSON RPC API that matches the reference implementations interface. So our goals for the future, obviously our main goal right now is interop, making sure that we can interop with mainnet and sync and validate all the blocks that currently exist is a huge benefit to the network. And then the things that we're working on in parallel, and stuff that we're getting very close to as well, is the miner integration and integrating with markets, which just basically means you're able to produce blocks and able to make deals with miners through using our node, and then also making sure that we have JSON RPC compatibility. So making sure that if you swap out the reference implementations node with our node, you won't be able to tell any difference from any sort of dev tooling or any usage of the RPC API. So yeah, here's the obligatory we're hiring slide. I made a little change just because I thought it was necessary. And yeah, that's pretty much it for me. Any questions?
Awesome. Thank you so much, Austin. You're an incredible engineer, and you and your team have done an incredible job with Forest. I'm sure the community is very eager to see it in production. So congratulations to you.
Yeah, it'll be exciting.
We do have a couple of questions. The first question comes from Jonathan. do you use or have you considered using the Tokyo runtime for async Rust, and why haven't you?
Yeah, so we definitely have considered it. When we started off, we definitely liked the long-term future of async SDD. We did consider Tokyo, but it was kind of a bulky runtime, and things seem to be moving away from that, especially with stable futures. It's definitely something. At this point, it's definitely something we wouldn't change. But I think we've definitely made the right choice. I mean, we've had great experiences with async SDD, and yeah, we don't really have any, I guess, plan to change it in the future. But yeah, we did very much consider it, and this fit way better with what we were doing.
Awesome, thank you so much. Another question here. Where do you see the most room for performance improvement in Forest, and when do you think we can start seeing Forest releases?
Yeah, so releases, I think releases are definitely going to, I'll just answer that second part first. I think releases will definitely come once we are syncing up to mainnet. We do have a few things we want to resolve, which should be resolved pretty soon, but hopefully we can start to see releases within, soon. I don't want to give an exact date. And as far as performance improvements, as you can see from Flame Graph, like I think the main improvement right now is just optimizing and making sure that the BLS signature verification is as fast as possible, and making sure that it's parallelized whenever it can be, which it pretty much is right now. But as you can see, it still takes a very long time. So I think targeting that is definitely the biggest thing. But there's still like small wins here and there, and we definitely want to be going a lot more into profiling in the future. So once we finish these immediate goals of interop, we're going to move definitely very quickly towards that.
Awesome. Thank you so much, Austin. I know you're a busy guy. Thank you for taking the time to speak with us today.
Thanks, Dustin.
Awesome. All right. We're on to our last presentation. Unfortunately, we had to make a slight adjustment to the schedule to conclude today's festivities. Juan Bennett from Protocol Labs has a scheduling conflict and has postponed to talk tomorrow. I definitely encourage everyone to tune in to tomorrow. We have another great lineup of speakers, another full day of blockchain presentations and conversations and discussions. But our audience is in great luck. We managed to get Eric to give a talk about Filecoin mining and his miner, Big Chungus TM. Eric, why don't you go ahead and turn on your cam and mic and join me on the main stage.
Is it working?
Hey, Eric.
Yo, what up? All right,
How are you?
Let's see if I'm going to be able to share my screen. Let's see if...
we'll see.
Fun issue for a lot of people today.
It has been, yes.
Oh my God, I have so many windows open. I have to choose a specific window. Allow. Oh. Wow, it works. Love me.
Awesome. Well, the stage is yours, Eric.
Perfect. I'm going to close. Stuff because I think I'm lagging hard. Okay. All right. Yep. So, hey everybody, it's Dustin.
Hey, Eric. It seems you're experiencing some technical difficulties.
And over the summer, our VP on this little project. So I'm going to give a quick, little TLDR of storage and mining. I'm not going to go too in depth about this because we have a lot of great speakers speaking about Filecoin throughout this week. But at a very high level, storage mining is almost like a useful proof of work. If you go a little technical, the analogy breaks down pretty quickly with expected consensus and pre-base time and all that good stuff. but at a high level, it's similar. In traditional proof of work networks, your I guess your power on the network is dictated by how much hash power you have. How much hash power you have is a function of how many GPUs you have, ASICs or whatever, right? In mining and on Filecoin, power is a function of how much hard drives you have, kind of, or more concretely, how much storage you're able to provide to the network. And so storage mining is like very easy to do simply, but very hard to do at scale, very solidly. So I mean, that's kind of the nice thing about storage mining on Filecoin is that, kind of anybody can get started. It's not like Bitcoin where you have to go to like some sketchy website and buy like these little ASIC things in Bitcoin and then mount them on this like shady rack somewhere in your closet. With storage mining, all of this is can be done, or rather has to be done on, regular hardware. So CPUs and GPUs that you buy from Canada Computers or Amazon or something like that. There's like no real way to do this using like ASICs. So Big Chungus is in the class of what we call small miners, despite our name Big Chungus. And we've kind of proven that small miners can participate effectively in the network, and yeah, that's been I guess what's keeping us going, and it's just fun to participate in such a big network. I think it's like at 1 exabyte or something like that. Like I don't even know how big an exabyte. I can't even picture how many hard drives that is. But we're a small fraction of that and contributing storage to that. This is kind of like a high level, basic level. Mining, or of a miner rather. So it starts off with mining, either accepting deals or pledging committed capacity. So to accept deals means to accept files, a price associated with the file, somebody who's willing to pay you, store their files on your system. Which is kind of the basic idea of Filecoin, and so when somebody when that deal gets accepted and you've accepted the terms and conditions of it, so the price and the time to store it for, you go to what's called the pre-commit phase of mining. This is also kind of known as sealing. So what happens during this phase is it goes through this algorithm which takes this sector of data and then creates a unique replica of it. And the unique thing about this process is that it's not parallelizable. So all of this has to happen on one CPU core, and it has to take a lot of time. That's kind of by design. Currently, sealing takes around 4 to do per 32 gigabyte vector. And there are items developed recently that have brought it down to 2 hours, which I think, this is just what I've heard, but I'm not entirely sure. I think that is the theoretical for, for a regular CPU. So after you've created this rep of this 32 gigabyte chunk of data, you go to what's called the commit phase of the process. And during this phase, you compute a snark of this and you commit it onto to prove that to prove to the network that you correctly run the sealing process. Obviously. After that, you're kind of good until 24 hours later. So every 24 every miner will have to complete a challenge, and this challenge is called a window post. Post stands for the face time. So every 24 hours, call will ask you to snark proof of a random sector that you've committed. and sure that are, in fact not cheating and deleting, sectors after they have sealed them on their drive. So this ensures if you've accepted a deal to store data for like 2 years or 20 years or whatever, that you're in fact doing that and not cheating everybody out. So just to go back with the pledge deals and pledging committed capacity, instead of accepting deals, you can also do as, just to kickstart yourself, is to pledge committed capacity. What this essentially means is that you have the ability to store data. So you're at this phase, you're kind of sealing these random bytes of data and upgrade later to store actual useful data. So yeah, that's kind of like the basics of a miner. There's obviously detail, tiny other things that you have to factor in as well. But at a high level, this is kind of what happens. So I'm going to talk a little bit more about Big Chungus in particular. If you look at that beautiful picture in there, that's me and David all decked out in our summer gear at the office. And that is our mining rig. When you normally think of mining rigs on blockchains, you think of like these gnarly racks with like 20 GPUs screwdrivered onto like a little metal frame thing. It's really scary to look at, and then like wires hanging out of everywhere. So those are our 3 rigs that we have for mining, and each of those rigs things, which I'll go into a little bit more detail in a second. So first off, I'll talk about our storage rig. So this machine, as you can see there, is the machine where we keep all of our storage. This machine has in it, and each hard drive can store 14 terabytes of data. So that's a lot of hard drives. It's actually a very, very heavy computer. So we have all these drives in RAID Z2, which gives us effectively 150 terabytes of usable storage capacity. Regular, off of Amazon Ryzen 7 processor that we got for like a few $100, 120 gigs of RAM, and over 10 gigabit Ethernet. So, as you can see here, like just very basic stuff that you can get off of Amazon. In our sealing machine, so this is the is in charge of the very CPU heavy tasks about before with the generating the replicas. So during the pre-commit phase. So this is the most specialized hardware we have, and it's not even that specialized really. It's like stuff you can get off of basically shops. AMD server processor in there, the EPYC 7F32. Over the summer, we had to like buy it off of like from Italy or Germany or something like that. But yeah, now that find them anywhere. This was 512 gigs of RAM. Has some NVMe drives, a little graphics. And yeah, our machine can seal around 6 sectors at a time. That's gigabyte sector, 180 something gigabytes at a time. Am I even doing my math right? 196, something like that. So yeah, for this it's a dual socket motherboard. So in the future, we can actually expand that and probably do like 12 or 14 sectors at a time. And then we have our snark box, which is in charge of the commit phase, the life cycle of mining. And this has very, stuff. It's just like an AMD Threadripper in there. And we have two GTX 2080 Ti. So during the generating snarks, you can very much benefit from having to do, like the computational proofs. So that's why we have two of these graphics cards in here. Just C1 in around like 40-ish minutes per sector. You can hardware. And so that we see this, pretty small setup. So we participated in Filecoin's Space Race 1. And during those 2 weeks, was it, or a month? I actually don't remember. It's like during the summer, and as years. Those few weeks, we still terabytes of capacity, and we've had of 99% and a retrieval success rate of 100%, which is very good numbers. We have enterprise level internet, enterprise powered machines off of one socket in the wall, 100 bit. We just have regular residential internet. Pretty impressive, in my opinion. And as of today, we have 21 terabytes of storage committed, and just to show you that actually make money now. Grants us a total of 110 phil in total rewards, and obviously that's we're only gonna get more. We're only gonna mine more blocks. So an interesting thing to see here is our power change graph. So this power change is essentially the growth of our miner and how much it's committed to the network over time. So as you can see, it's quite linear with some in between. These are, just stupid failures on our part while we're running it during the incentivized testnet. And recently, Filecoin has some issues with, very high gas prices, like basically every other blockchain. But sometimes we have trouble getting our messages through the message pool, or what most people know as like the mempool. But we've recovered quite well from it. We've recently set up logging infrastructure and alerting and all of that. So I don't stay up until like 4 a.m. Just refreshing this miner page anymore, or checking or SSHing into our node. Now I stay up until 4 a.m. watching YouTube videos instead. So yeah, at first Big Chungus was kind of like, a hobby project that we kind of did for fun, but, very quickly we realized Big Chungus is actually quite important for, our organization and, a few of our teams. As, Austin just talked about, our team is working on Rust, which is the Rust Filecoin implementation. And obviously, he talked about the importance of having multiple different implementations on the network, but we also kind of want to differentiate ourselves from the other implementations as well, and provide offerings that that a reference implementation like Lotus might not consider doing, because their goals are very much different from our goals. So Big Chungus was a very good opportunity for us to explore different stakeholders in the Filecoin ecosystem and understand other needs when building, software for Filecoin, and obviously in particular the miner ecosystem. So me and David, we've learned a lot from this whole project, and this will obviously translate very well into how we build Forest, textures that we choose, and the next iterations of Forest. Yeah, Austin should have talked about some of this a few minutes ago. We're also working on like Big Chungus is also going to be quite useful for when we're testing out our retrieval market stuff that I think David will probably talk about sometime tomorrow. David or Elizabeth, they're working on very cool stuff related to secondary retrieval. Big Chungus will play a big role in tech for those for all of the Filecoin software that we're. So yeah, that's kind of the future for this. Providing support for other Filecoin projects that we're building and learning more stuff about being a miner. Right now, a storage miner, and then hopefully also being a retrieval miner. Yeah, that's kind of it. There's a picture of me and David again. If there's any questions that you have related to Filecoin mining, being a small miner on Filecoin, and how to get started and all of that, like definitely hit me up on Twitter. Link is down there. Please like, subscribe, check out the comment section. Yeah, that's it. Thank you.
Awesome. Thank you so much, Eric. I know it was last minute, so we greatly appreciate your participation. It was a great presentation, and I think we all appreciated it.
Yeah, no problem. This is fun.
We do have a couple questions for you in the Q&A. First question, what was the hardest part to source?
Yeah, I mean, the hardest part to source was definitely that AMD EPYC CPU. It was, I think it came out officially in April or May or something, and we started building this in July. And dude, like the whole supply chain in computing is like a mess right now. It's like impossible to find a lot of CPUs or GPUs. And so the special thing about these 7F series CPUs is that they are the high frequency equivalent of a lot of the AMD EPYC line of CPUs. And the reason why you want a high frequency CPU for this is because, like I said, during the sealing process, like things cannot be parallelized. So it means if you have to do things sequentially, you better be able to do them really fast. So these were impossible to get. We had to, like I said, we were looking on eBay. We bought it from like some random store in Germany. It's just funny. But yeah, that was probably the hardest part to source. I think they're much more readily available now. I saw them a lot Canadian retailers recently, so yeah, it shouldn't be too much of an issue anymore, hopefully.
Awesome. This question just jumped up on our board and got many votes really quickly. What's the story behind the name?
There really isn't any story. I think Big Chungus has just kind of been a meme that we have at ChainSafe among a few of us. We just call each other Big Chunguses, and yeah, I don't know. It's just a funny meme. Like, it's funny. Like, don't you think it's funny? Just a fat bunny.
Awesome. In hindsight, what parts would you have bought differently?
Yeah, I mean, that's a good question. Certainly, so within our storage box, right now we have a motherboard that has like 3 PCI X16 slots. We really should have tried harder to find a motherboard with 4 PCI X16 slots. So 3 of those slots right now are taken up by SATA controllers. I kind of want to throw in a GPU in there, but it's like I can't because there's not enough slots. And the reason why I want a GPU in there is to do these 24-hour proof of spacetimes faster. Right now, every 24 hours, our CPU is bursting up to 100% on all cores, computing the snark proof. It's like, I mean, it's doable, but it's just a little uncomfortable. It's like very much possible to miss a deadline by accident if it takes a little bit more time. Also, I guess another choice. I mean, this is not something I would have done differently because we didn't really have an option. But kind of like 2 or 3 months after we bought all 3 of those 2080 Ti's for a lot of money, the 3000 series GPUs came out. So it was kind of that kind of hurt a little bit, but not so much because it's possible to get your hands on those anyways. So yeah.
Last question for you. Do you plan to use Forest on Big Chungus?
Oh yeah, 100%. As Forest becomes, more production ready and ready for testing, we're gonna, swap out Lotus for Forest. I mean, if you're building something, you better put your money where your mouth is, right? We have real money sitting on these machines, and we're building software. And if we can't trust our own software, how are other people supposed to trust our software? So, after we're ready to release Forest, after it's all tested and productionized, we're swapping, we're going to slowly start swapping out all the Lotus components from our system and putting in Forest. In the future, when we build our implementation of the storage miner in Rust, going to swap that out as well. Yeah.
That's awesome. Thank you so much, Eric. It was a pleasure. I know you're busy, so thank you for taking the time.
Thank you for having me.
Absolutely. With that being said, all right. So, ladies and gentlemen, that concludes day one of CSCON. Thank you so much for attending, listening, and engaging with presentations. We have another amazing lineup of speakers ready for tomorrow. Please come back and tune in. If you haven't done so already, give ChainSafe a shout out on Twitter. I know you're on Twitter. Use the hashtag CSCON. Give us a shout out. That'd be greatly appreciated. Lastly, if you are a developer interested in blockchains, please check out our career page on our website. There you'll see a number of open positions. And I have to tell you, we do some amazing work, get to work with some of the best people around. Please go check it out. My name is Dustin Brickwood. It's been a pleasure emceeing today. I look forward to seeing you all tomorrow. Thanks and have a great day.